Did you know in 2009 Usain Bolt, the sprinter from Jamaica, set a new world record for the 100-meter run? He ran it in just under 10 seconds, 9.58 to be exact. That's absolutely flying at a rate of about 25 to 30 miles per hour, which is faster than I can ride my bike. It's faster than I drive most days. In fact, if you take a look at our graphs of our distance over time, you'll see that Usain Bolt, here graphed in the green, and mine in the blue are a little bit different. He runs at a much faster constant rate. The slope of his graph is much steeper than mine. And that's the reason why if we were to square off in a race, Usain Bolt would absolutely crush me. In fact, I would need about a 30-meter head start in order for our finish times to be about equal. If I slide my blue line up, giving myself a 30-meter head start, you can see that at the rate of speed that I run and the rate of speed that Usain runs, we'll finish at about the same time. However, I think he's still going to edge me out by just a little bit. All right, let's take a look at today's lessons in which we talk about constant change and the graph of the equation y equals mx plus b. Today we're taking a look at linear functions and the graph of linear functions. Simply put, the graph of a linear function is a straight line. It's going to have a slope and it's going to have a y-intercept. And we are going to be graphing the equations that are in slope-intercept form. So over here in my Desmo sketch, you'll notice in box 1, I have y equals mx plus b graphed, where I have sliders for m, my slope, and b, my y-intercept. So as soon as I start to drag that slider, you'll see the slope of that line change. As well as if I drag my slider for b, you'll see my y-intercept change. Now this is known as slope-intercept form because what we're doing is we're graphing a line based off of its slope m and y-intercept b. The y-intercept is the point at which it passes through the y-axis. Now notice this is also where x is equal to 0, and you can see that right here in our table where x equals 0. This is where our y-intercept is. Also recall that our slope can be calculated from any 2 points on that line. Your slope formula you've noted is y2 minus y1 over x2 minus x1, also known as the change in y over the change in x. Or maybe you've referred to it as rise over run. And I'm going to misspell rise here on purpose just to remind you that the y's need to go on top. So in order to calculate the slope, I can pick any 2 set of points such as -2, -3, and 1, 3 to calculate this slope. I should end up getting a slope of 2. Now also keep in mind, besides having a y-intercept, we're also going to have an x-intercept. So we're going to go ahead and change our graph here a little bit. We'll change our slope. Now you can see that we have a y-intercept of +2, but we also have an x-intercept of +2. And just like the y-intercept is where it crosses the y-axis, the x-intercept is where it crosses the x-axis. And you guessed it, this is the value where y is going to be equal to 0. And again, you can see that down here in our chart. All right, let's take a look at a few examples for today. A pool contains 85 gallons of water already. Suppose a hose adds 7 gallons per minute. We want to write an equation. This is going to be a constant rate of change equation that represents the amount of water in the pool t minutes after the hose is turned on. So let's let g equal our number of gallons, and t is our time in minutes. It's always important to set up our variables before we get going. So here we go. We're going to write our equation now. Our g, our number of gallons, is going to be equal to 85, that is already in there, plus 7 gallons per t minute. So we're going to increase at a rate of 7. 7 will be the slope of this equation, whereas 85 will be my y-intercept. In example 2, we read that we have a mudslide that left 42 acre-feet of mud in a valley. Sounds like a lot. I have no idea what an acre-foot is. The mud is being removed at a rate of 5 acre-feet per day. Let's write a linear equation to model a situation. So we're going to let m be the amount of mud in acre-feet, and we're going to let d be the number of days. So when we write our equation, we can write this in function notation that says m of d days is equal to the 42 that we start with, and now we're removing, so we're subtracting 5 acre-feet per day. In part B of this question, it asks, when will the mud be removed, completely gone? In other words, when will m of d be equal to 0? So let's set 0 equal to 42 minus 5d, and we'll solve for d, the number of days it will take. We're going to first of all subtract 42 over to the left side, so we'll have negative 42 equals negative 5d, and when I divide both sides by negative 5, I get the number of d days to equal 8.4. So after 8 days, between the 8th and 9th day, all the mud will be removed. Now it says, what is the y-intercept and the slope that are represented by this equation? Well, our slope here is the amount of removal per day. Now that negative is attached to that 5 because we're going to have a slope that's negative 5. And our y-intercept is how much we start off with, and that's 42. Now we're being asked to graph this line and indicate the point that indicates no more mud is left. So remember, on the y-axis goes our dependent variable, and that's the mud based off of d days, and then along the x-axis is our independent variable. That's going to be d for days. Okay, now that we have our axes labeled, we can go ahead and start plotting some points. If it helps you, you can always make a table of values. So if you do something like this, we can start substituting in 0 days, 1 day, 2 days, 3, 4, so on and so forth. Well, at 0 days, we know that there was 42 acres of mud left. After 1 day, there's removing 5, so we'll have 37, and then 32, 27, 22, so on and so forth. Let's go ahead and plot at least half of those points on our graph here. All right, you can see that I went ahead and plotted about every other point here. I know it's sloping down at negative 5, or another way to do that is every 2 you're going to go down 10, and therefore we see that right here, just between the 8th and the 9th day is the point in which they're going to have that mess totally cleaned up, and there'll be 0 acre-feet of mud. All right, in example 3, we have a very realistic situation here. Rick gets an allowance of $15 per week. A little steep in my book, but whenever his parents pick up dirty dishes, he has to pay 30 cents. In other words, he gets fined 30 cents per dish. Don't cry about it, Rick. Just pick up your mess. All right, we want to write a linear equation here that models this situation. So we're going to say A, the amount he has, is equal to $15 minus the 30 cents that he gets charged per dirty dish. Just pick up your stuff, Rick. You'll be fine. How many dishes will it take for Rick to earn $0? In other words, be a complete slob? Well, we're going to let 0 equal the amount, set that equal to his $15 that he starts off with, and we're going to subtract 30 cents per dish, and that's how much we want to find. Let's move 15 over to the other side of the equal sign. So we'll end up with negative 15 is equal to negative 0.3d. Divide both sides by negative 0.3. And when I do that, I'll end up with 15 divided by negative 0.3, and that gives me a total number of dirty dishes to be equal to 50. That's a lot of dishes, Rick. All right, what are the y-intercepts and the slopes that are represented in this equation in part A? So let's come back up here. Our y-intercept is how much he starts off with. He starts off earning $15, so that's our y-intercept. Our slope here is the constant rate of change, which in this case is going to be negative 0.3 based off of the number of dirty dishes he leaves laying around the house. All right, take a second, label your axes. Remember, along the y-axis you have your dependent variable. The amount he earns is dependent on the number of dirty dishes he leaves laying around the house. Finally, for today, we have a theorem from geometry, parallel lines and slopes theorem. Remember, two lines are parallel if and only if they have the same slope. That means they're increasing at the same rate of change, or they're decreasing at the same rate of change. They'll never intersect. So over here on the right hand side, you see a picture of that. These two lines have the same rise over run, and therefore they are never going to intercept each other. All right, here's a final example. We want to find the slope of the line between points A and B, and find the slope of the line between points C and D, and tell if these lines are parallel. So we'll use our slope formula to calculate that slope of AB. We get negative 7 minus 5 is negative 12 over negative 4. That simplifies to 3. The slope of line AB is 3. Let's calculate the slope of line CD. Since they both come out to equal 3, we know that they have the same slope, and therefore they must be parallel lines.